Socket programming. You want to build networking applications, you will need to know this. Most of the material that is covered as part of the slides is taken from this particular reference. I will provide a PDF copy of this for you. So let's start out with this quote. I hear and I forget, I see and I remember, I do and I understand. So no matter what I say in this video, unless you actually do it, things will not be clear. This video is mainly to give you a head start to get you started on this topic. Do you will, since there is a project on this topic. We covered this aspect before. Applications interact with the transport layer through a socket. And there are certain fields that are important to facilitate this communication. One is the source port and the destination port. A few other fields that are important also are the source and destination IP addresses. So what is a socket? Basically, it's an interface between an application process and a transport layer. So a process, the application process, will use a socket to send, receive messages from another application process. And this other application process could be local within the host, or it could be a remote host. Often when you're doing socket programming, you start out with a local process because this is easier. Later you can extend it to other hosts. So Unix jargon, a socket is nothing but a file descriptor, an integer associated with an open file, and you write into this file and you read from this file, the application processes, that is. So there are many types of sockets. There are internet sockets, there are Unix sockets, and there are X.25 sockets. We in this video are going to focus exclusively on internet sockets, and these internet sockets are characterized by the IP addresses and port numbers. IP addresses are 4 bytes, port numbers are 2 bytes. So when you're building applications, you basically work in the user space, that is where the processes run, and they interact with the transport layer, which is running in the kernel space. And transport layer in turn may make use of other layers like network will make use of link. All these work in the kernel space. Within the internet sockets, there are two other types. Stream sockets, these are connection oriented sockets. Basically, when you open a stream socket, underlying you use TCP protocol to provide reliable two-way communication. The other type of internet socket is a SOC datagram socket. This uses UDP protocol. In this case, there is no reliability. Before we proceed further, it is important to understand this. There are two types of byte ordering. The big Indian, this is also called network byte ordering. In this, the higher order bytes of a number are stored in memory at the lowest address. And little Indian is the opposite, where the lower order byte of the number is stored in the memory at the lowest address. Some hosts use this ordering. So the networking protocol stack TCP/IP expects everything to be in network byte order. So if you don't ensure this, there will be a lot of confusion. So when you're doing socket programming, it is important to ensure this. And there are a few functions to help you in the process. HTUN stands for host to network short, host to network long, and similarly network to host short and network to host long. So what these functions do is when you give them an argument, they will convert it from the host byte order to the network byte order. When you're writing an application protocol, you can go for a connection-less protocol or a connection-oriented protocol. I'll get to that shortly. In connection-less protocol, you basically use UDP as your transport protocol, and this is the typical structure. So there are two endpoints. You can call them different hosts or a server and a client. And these two endpoints are going to open a socket, and then they are going to bind their IP address and whatever port on which they are going to listen to this particular socket. So binding is a process where you give the identity to the particular socket. That is, associate the socket with a given IP address and a port number, And once you do this, then both these hosts are free to communicate with each other using these functions, receive from, send to, and so on and so forth. And once they are done with the communication, they can close the particular connection. So this is just an overview. We will see more about all these functions shortly. Similarly, at the application layer, you can also implement a connection-oriented protocol. In this particular case, there is a server that is going to listen on a specific port. For this, you open the socket, you bind the socket with a specific port number. For example, if this is a web server, you will bind this particular socket with the port number 80 that corresponds to the web process. Then you listen on this particular socket. While you are listening on this particular socket, the other endpoint, the client, which would also open a socket, and then it will connect to this particular port. And as a result of it, you accept this connection, and after this point on, you can both send and receive data. And once you are done, again you can close this connection. By the way, this specific structure you could use with both UDP as well as TCP. If you are using UDP, there is no reliability provided. When you are using TCP, there is underlying reliability provided. Also, when you are using UDP, you can get, as long as all the clients are using the specific port on which you are receiving, you will get the information from all the clients. So at the application layer, you have to sort out the connections and accordingly reply. Whereas for TCP, you will get separate sockets for each incoming connection. We covered this as part of connection-oriented multiplexing and connection-less multiplexing. So how does one open a socket, that is get the file descriptor corresponding to that particular socket? So this is the function that is used. So let's look at each argument in turn. So the domain, since we are dealing with internet sockets, we will set it equal to this value. And this type field, you could set it either to sock stream, in which case you are using TCP, or sock datagram, in which case you will use UDP. Typically, the protocol value is set equal to 0 to let the correct protocol be chosen based on the type value. So as a consequence of executing this socket command, the socket returns a socket file descriptor which you are going to use later. If there was an error, it will say -1 on error. So this is the usage. So you are assigning sockfd to integer, and then you are calling this particular function and assigning whatever value it is returned to this sockfd. This function just gets the file descriptor. Now you have to associate with this file descriptor some identifiers to identify the particular socket. So the function that is used there is the bind function. This is used to associate a socket with a port on the local machine. Once you do this, the kernel will then match an incoming packet to the write process. So this is the process of demultiplexing. To bind, you need this particular function. So you are binding certain identity to a socket. You specify the identity of the socket using this argument, and then you use the structure sock address to specify information to which the socket has to bound to. So this sock address, my address here, is a pointer to a structure sock address that contains information about your IP address and the port. And this address length is nothing but the size of this particular structure. Again, when you call a bind, if this bind was successful, it will return a 0, otherwise it will return -1. Again, a few words of caution here. All ports below 1024 are reserved. So if you try to bind to a value below this, you will get an error. You can use ports above 1024 up to 65,535 provided they are not already in use. Suppose you are coding up a server and you have bound the server to some port, say 5000, and you kill the server and restart it. When you restart the server, it may result in a bind failure. Why will this happen? Because the socket is still in the kernel using that port. Why this occurs, we will cover it when we cover the TCP protocol. But for now, a way to get around this is if you just wait for a minute or two, the socket that is still in the kernel will get cleared up, Otherwise, if you don't really want to wait for this much time, you can use this function set sock opt to clear the socket. I will leave it for you to look up on how to use this function. So this bind function is making use of this structure. So let's look at the structure in a little bit more detail. So this structure holds socket address information for not just internet sockets but for other type of sockets. In turn, it is made up of these two fields, SA family and SA data. So if you are using the internet family, you will set it equal to INET. But since we are interested in the internet socket, there is actually a parallel structure that is used to reference elements of the socket address. So this is the parallel structure, where in turn it has four fields. One is the SYN family like before. Here it is set equal to AFINET to refer to the internet socket. And then you can specify the port information, you can specify your IP information. If you see here, this is 14 bytes. So the port will be 2 bytes, this one will be 4 bytes, so that is 6 bytes overall. The remaining 8 bytes are set equal to all zeros as far as the internet sockets are concerned. And again, let me emphasize that this port information as well as address information must be in the network byte order. This, by the way, can be in host byte order because this is not actually sent out in a packet, whereas the port and the address information are sent out in a packet. So these are all again regular standard short, unassigned short character. So there is another structure called structure in address, that is the internet address. Let's see at that structure first. So this structure is made up of one field, unsigned long S address, which is 32 bits long. Now how does one populate these structures? So basically this is how it is done. So you're defining the structure sock address in, and this is the name given to it. So in the family, I'm setting it equal to AFINET. The port, I am going to set it to my port. So there is something defined that my port is, let's say 80, in which case it is going to set it equal to that value. Notice that I'm converting it from host to network byte order. And similarly, there is this very useful function called inet_aton. This stands for ASCII to network. So you can just specify an ASCII field like this and give the address, and it will convert this ASCII field into the right structure. And this is how I set zeros to this particular field within the sock address in structure. By the way, this particular function, if it were successful, it will give a non-zero. If there was a failure, it is going to give 0. There is a reverse function to A to N called N to A. This is network to ASCII. So if you want to print this particular information that is stored, you can use this function to print it out. Again, two other useful things to know. Suppose you don't want to choose a port, you just want the kernel to choose a port for you. You can set it equal to 0, in which case an unused port is chosen at random by the kernel. Similarly, if you don't want to be bothered with setting this internet address, you could set it equal to this, in which case the kernel will set it to the correct IP address corresponding to your host. So let's see whatever we have learned so far through this code snippet. So I am defining an integer sock FD. This is where the file descriptor corresponding to the socket will get stored. I am also defining an address field, and then I am opening a socket and I am storing the file descriptor in this, and then I am going to fill my port and address information in the sock address structure called my address. So this my address family, I set it equal to this port. I'm going to set it equal to my port. Again, this is defined somewhere, and I'm going to set it equal to this particular IP address. So that is shown here, and I'm going to set the remaining values equal to 0 using this memset command, and then I am going to bind this open socket with this information which is related to my address information. After this, if you are using the connection less approach, you could use UDP sockets and communicate between the two endpoints using the send to and receive from functions. So let's see these. So in this case, there is an assumption that this socket, when you opened it, is of the UDP type, that is the datagram socket. If you want to send a packet, you just need to use this particular command send to. So you're specifying via which socket to send this packet through, and then you are specifying what message to send. So this is the pointer to the data you want to send. This length here corresponds to the length of the message. For now, we will ignore flags, we'll set them equal to 0, and then you're specifying another sock address called to, where this is a pointer to a struct sock address which contains the destination IP and port. When you're using this send to function, you have to clearly specify who the endpoint of this particular packet is, since we are using UDP protocol. So for this, all that information has to be populated in this particular structure called to and given in here. And to length is the size of this particular structure. So once you call send to, it returns the number of bytes actually sent or -1 on error. Again, a very important point to note here is you may send 500 bytes, but actually the send to function may have sent only 400 bytes. In which case, in this return field, it will specify it as 400 bytes. So you need to keep track of how many bytes were sent, and then accordingly the next time you will have to send the 100 bytes, the difference between them again. The transport protocol is not going to keep track that I have sent only 400, 100 are remaining and resend it. That's not its job. It is a job at the application layer. So you have to keep track of what was sent, what wasn't sent, and accordingly send information later. So receive from is a function that will help you get a packet from the transport layer. So again, this is the socket from which you are receiving this particular packet, and this is the buffer from which you can read information, and this length n refers to the maximum length of the buffer. Again, flags, we will set them equal to 0, and this field from is populated with the IP address and port of the other endpoint. That is, whoever has sent this particular packet. The source IP and the source port information is filled in this from. This sock FD refers to the destination. This refers to the source. And this function again returns the number of bytes that were received. Once you are done sending and receiving data, you may want to close the particular connection, in which case you can use this. So when you do this, it closes the connection corresponding to the specified socket descriptor and frees up the socket descriptor so that it can be reused again later. And once you close a connection, you cannot do any more sends or receives. The same figure I have shown before, I am reproducing here to put it in perspective. So the server opens a socket, it binds to a given port on which it is listening. Similarly, the client also opens a socket, it also binds to a given port, let me say port 2. Somehow this end as well as this end know which port information to send. So when they send this data, they will specify what the destination information is, in which case server will specify the client IP address and the client port information. Similarly, when this should refer to this, and similarly when the client is sending information, it will specify the server IP address as well as the server port, which is port 1 in this particular case. And once you receive a packet from this end, where you receive from information is filled up in that from field and passed to the application. A good time to break before we get into connection oriented protocols. In connection oriented protocol, as mentioned earlier, the different process is followed. So you have socket bind listen, and this other end doesn't bind because it is not necessary to bind here, because you are the one who is initiating the particular connection. You are not listening as such, you are sending a packet to the other server. So the server has to bind because it has to listen on a given port. Here you are not listening. But when you do the connect, some socket is actually opened and information about this particular connection is associated with this particular socket. We'll get to that shortly when we cover the connect function call. And then once this connection comes, you're going to accept it. From this point on, you can then again use send receive to exchange information. Once you're done, you can close the connection. So let's see these new functions: connect, listen, accept, send and receive. So connect is used by a client to connect to the other end, often a server. So this is the function. You have to specify on over which socket to connect, and then you again have to specify the other endpoints information. This is the server information. So you need to specify the destination IP address and the port information. And this address length is again the size of the structure. If things didn't go well, this will return -1 on error. When you do connect, there is really no need to bind. This particular socket FD, when you do the connect, based on this information, since you're using a TCP as your protocol, it knows the destination IP address, destination port. It will choose a random port as the source port, and it already knows the source IP information. So this 4 tuple, it is going to associate with this particular socket when you call the connect function. So nothing like an example. Let's again look at an example. Here I'm specifying that this is my server IP address, the destination IP address. This is the destination port. This code is specific to the client process. So I'm first going to open a socket, and I'm saying that this is a TCP socket, and I'm going to fill in the destination information where I've specified the destination port, the destination IP address. I've also set equal to 0, and then I'm saying connect over the socket to this particular destination. And as a consequence of this socket will be associated with the 4 tuple corresponding to the source, that is the client's IP port information, as well as the destination IP and port information. In this particular case, it will pick a random source port. By the way, bind is optional here, but if you really want to use bind because you want control over your port information or the IP information because you have multiple interfaces, you can use a bind before you call connect. So the client did a connect. Now the server side has to listen. So this is the function that it uses. It waits for incoming connections. This function is rather simple. You specify the socket on which to listen, and you specify the number of connections that are allowed on the incoming queue. So this server is going to call a listen. Later it will call accept to accept this incoming connection. But before accept is called, there may be multiple incoming connections, all of which are queued up, and this backlog specifies how many connections are allowed on the incoming queue. If it exceeds this number, then connections will be dropped. Again, listen returns -1 on error. Again, important point to note, you have to call bind before you can listen because you need to specify information about the port on which you should listen. Accept is a bit more complicated than listen. So after you listen, you call accept, and what accept does is it gets the pending connection on the port on which you are listening. So this is the port on which you are listening, and information about this incoming connection, that is the IP address, the source port information, is stored in this address field, and address length is set to the size of this particular structure. And this is what is interesting, in that once it accepts a new connection, it is going to return a new socket file descriptor that will be used for this accepted connection. Now notice there are 2 socket file descriptors. One is this original sock FT based on which you are listening, and this is a new socket file descriptor which will you use to send and receive data. Again, an example helps. So in this particular case, this is from the server side code. So I have opened a socket. I am also giving a new socket for the new incoming connection, and this is my address and this is the other end's address. I'm just defining these structures now, and then I'm going to open a particular socket. This is a TCP socket that I'm opening. Remember, you have to bind that particular socket to your information. So my address information, my port, I will pick up my own IP address, and I'm going to bind my address to this particular socket. Then I'm saying listen on this particular socket. Then I'm going to call the accept function, which when there is a new connection is going to return, and it is going to tell me the information about the new connection. So this is the client information that will give, and along with this it will give me a new socket file descriptor. So henceforth when talking with this particular client, the server is going to use this socket. So the send and receive functions are used for communicating over either stream sockets. They can be used over datagram sockets, but these have to follow that bind, listen, accept paradigm, in which case you can use send and receive. Again, the send function is simple. You are specifying the socket through which to send the data. You are specifying a pointer to the data you want to send, the length of the data in bytes. Again, we will not look into flags. And this is going to return the number of bytes actually sent. And again, remember that this may be less than the number you told it to send. You as an application developer have to keep track of it and accordingly send the next data. So here is a simple example that captures it. So this is my message that I want to send. So there is a lot of socket opening code that is not shown here. So this is the socket through which I want to send this message, and I'm specifying the length is nothing but the string length of this message, and this is the flag information. And this returns how many bytes it actually sent. So both the server and the client are going to send, and both of them are going to receive. So the receive is the function based on which you receive the data. Again, you're receiving on a given socket, and this buffer is the buffer to read the information into. Length is the length of the buffer, and again we'll set flags equal to 0, and this receive function returns the number of bytes actually read into the buffer, or -1 on error. If this receive returns a 0, that indicates that the remote side has closed the connection on you. So this is used to figure out whether the connection is closed or not. Again, flashing what has happened. So the server will open a socket, it will bind the socket to a given port on which it is listening. If it's a web server, it will listen on port 80, and then you listen on this port, and whatever connections are coming you accept. After this, you are going to send and receive information using these functions. Once you're done, you close the sockets. Whatever code snippets I have shown so far are for a single client. Managing multiple clients is a little bit more complicated. I will get to that shortly. Before we get into a few additional miscellaneous functions as well as a little bit more complex scenarios, a good time to break. When you're doing socket programming, there are a few miscellaneous routines that can make your life easy. One is something called get peer name. Often you want to know for a given socket descriptor who is at the other endpoint. You know who is at your endpoint because you have specified the particular port or the address information. Often if you want to know who is at the other endpoint, you can use this function to get that information by passing on this structure where the necessary information gets filled. At times you want to know the name of your computer on which your program is running and store that information into the host name. For this you can use this specific function called guest host name, and that name is stored in this particular pointer. Sometimes when you're doing socket programming, you want to work with host names. For example, if you want to communicate with the given server name, so this is the server that you want to communicate, then your code has to figure out the IP address that corresponds to this, for which you need the DNS service, for which you can use this particular function get host by name. So this is the structure that it uses. It specifies the name and the list of network addresses associated with this particular host. Again, an example helps. So for example, you want to know what is the IP addresses associated with this particular host. You will do get host by name, you specify the string, and you can print what the name is using this command printf, and you can find out what the IP address that is associated with this by doing the appropriate conversions. So there's a lot of typecasting involved here. A server often has to handle multiple clients, in which case you use these functions accept, receive. A point to note is these functions accept, receive are what are called blocking functions. By blocking, I mean they will not return until some event has happened. Suppose you are a server that you are listening on a given port and you have accepted earlier some other clients, let's say client 1, client 2. Now to receive data from these clients, you are going to call the receive function, and to accept new incoming connections, you are also going to use the accept function. Both these block. In other words, if you are waiting for accepting a new connection, if this client want to send data, you are not going to serve it because you are blocked on accept. Similarly, if you are blocked on receive, waiting for data from say client 1, if new connections come, then you can't accept those new connections. So this is a difficult problem to handle. So one way to handle it is to make sockets non-blocking. This you can do using this function called fcontrol. So if you set it equal to non-block, the socket is no more blocking. But then you have to poll the sockets to see if something interesting is happening on the particular socket. That is, whether you are receiving a new connection or you are receiving some data. This polling is very wasteful of the CPU time. It slows down the server process significantly. So you don't want to do that. The solution there is to use this select system call. This is highly recommended. I will get into the details of this shortly. Another thing which you will have to handle when new connections come is whether you want to fork a separate process for each incoming connection, or you want to handle it as part of a new thread, part of the same process. Again, how to do this, I will leave it for you to figure it out. But let me cover a little bit more about this select system call. Looks slightly complicated. So this select call has lot of arguments. So this number FDS specifies the highest file descriptor plus 1. Basically, to this select function, you are going to give a list of file descriptors for it to monitor. So you can monitor the file descriptors as read FDs, write FDs, and accept FDs. Basically, it is monitoring for read operation, write operation, or exception operations. So this select function, you are going to specify these set of file descriptors. There are different sets for each of this read, write, exception operation. And now what the select does is, whenever there is some event, it is going to return and it will modify the set to indicate what has happened. So in this case, you could give a list of all the sockets. For example, the socket on which you are listening, that client 1 socket on which you are receiving, the client 2 socket on which you are receiving, so on and so forth. And this one, when it returns, for example, if it's a new incoming connection, it will return the socket corresponding to the listen on which you are listening. On the other hand, if it were a data that you have received corresponding to client 1, it will specify this particular socket corresponding to client 1. Then you can take corrective action and again call select for it to monitor the sockets. So when you do select, you can also specify after a period of time if there is no action for it to return. So this times out and it returns after this particular time. So that way select also blocks. And if you don't want it to block indefinitely, you can use a timeout value for it to return. So this number FDs here is going to capture whatever is your value of the highest file descriptor. You have to add a value of 1 to it and pass it as an argument here. Again, I think a simple example will help understand the select concept. Before I get to that, here are some useful macros. If you want to clear a file descriptor set, you can use this command. If you want to add a socket file descriptor to a set, you can use this particular command where you are saying to this set add this particular socket descriptor. If you want to remove a file descriptor from the set, you can use this command, and if you want to see if a file descriptor is in a set, you can use this particular command. So here is a simple example. This, by the way, has no relation with the server client concepts that I have covered before. In this particular example, it just tries to figure out if a key on the keyboard has been pressed or not. So for this, I am defining the standard input. So this is the file descriptor that corresponds to the standard input. So this is the main call. I am specifying a timer value, and I am clearing out I'm setting to 0 the set of file descriptors, and I'm adding this standard in to this particular set. And I'm asking select here to monitor for read operation. Note that the write operation as well as exception operation, I have set it equal to null, and I am giving this number of Ds to this +1, because as I said, that's what you have to set it equal to. And I'm also specifying the timer value. Now if indeed some key was pressed, the select will return, in which case I'm going to compare whether this stdin is part of the set of file descriptors, in which case I'm going to say the key was pressed. Otherwise, if it were to return, that means that set is null, which means it happened because of the timeout operation. I think I'll stop here. Some things you should learn on your own. There's only so much spoon feeding one can do. So here is a summary of what all we have seen. Sockets help application processes to communicate with each other using standard Unix file descriptors. There are two types of internet sockets: sock stream that supports TCP and socket datagram that supports UDP. We have seen quite a few functions that help in the process of socket programming that let you write very interesting applications. So good luck with the project and have fun coding. Here are a few quick references. There are quite a few books on network programming. So Richard Stevens is a pro in this area. Beat's Guide to Network Programming is in fact quite a fun read. All these slides were followed based on the 2001 version. There is a very recent 2012 version that includes IPv6. You can follow either version, but I think 2001 version will make it easier for you to understand what has been covered so far.